Hey guys, this is Ed from Mission Ed Possible. Today we're going to be looking at Atari 8-bit assembly language programming. Recently I've been doing a lot of Atari 8-bit assembly programming, and I've gotten to a point where I thought I'd maybe create a series on how to do it. I've watched several different tutorial videos, I've read lots of things online, and a lot of the tutorials that I found don't actually show a full game creation process. It'll show a few bits and pieces, and you're kind of meant to fill in the blanks. And unfortunately, some of that is kind of annoying because you may not know how to fit everything together. That's one of the things that I struggle with a lot starting out. The goals of this are to actually make a game from scratch to where it's actually playable. And the kind of game that I'd like to make here is a roguelike. If you're familiar with the game Rogue, you know that it's a procedurally generated world. Rogue is a dungeon crawler. I'd like to create things like towns, vendors, things like that. I do know that we're going to have some problems with limitations with RAM and stuff like that. I have some ideas on how we can alleviate some of those. Why the Atari 8-bit? There's a lot of people that are going to say, well, why aren't you doing this in Unity, or why aren't you doing this for a modern platform so that it'd be more accessible? And it's like, the deal is that I grew up with an Atari 8-bit computer. It was my first computer, and I learned how to program in BASIC, but I didn't ever learn how to do it in assembly, and I didn't have any books or assemblers or mentors or anybody to help me. So, 35 years later, and I actually know how to do some of this stuff now. So this is sort of a checkbox for, a life checkbox for me. I know there's a lot of people that probably are in the same boat as I am, and a lot of this stuff is a mystery. So hopefully I can take you on this journey and you can learn something, and I'll learn some stuff along the way as well. That being said, I am not an expert at this by any means. And so there's probably going to be some things in here that I'm doing incorrectly or inefficiently. And if you see something, definitely call it out. I am still learning a lot of this stuff. I have quite a bit of experience with assembly language, not specifically with 6502, but with assembly language in general, mostly x86 assembly. This will be an interesting project. One of the things that is interesting also about doing stuff with a older platform like this is that there are a lot of limitations. You have a certain amount of colors you can use, you have a certain amount of pixels you can use. And so there's a lot of things that you have to do differently when you're programming for a old platform like this. There are some things that make it a lot easier for people that are not pixel artists. If you're a pixel artist, you could definitely make use of a 32 by 32 tile size and, millions of colors and stuff like that. But here's the deal. We have, for what we're going to be doing, we have 8 by 8 tiles, and actually 4 by 8 tiles, and 5 colors maximum. So that's going to be challenging, and there are ways of increasing those numbers, especially with the colors. We're going to try to keep it simple for the most part, and who knows, we might get into more advanced stuff to be able to do more colors. For now, I want to keep it pretty simple and actually get something working. What do you need to know to be able to do this? You should understand hexadecimal and binary numbers, and basically how they're represented, and because we're going to be using a lot of binary and hexadecimal here. I don't expect you to know a lot of assembly language. I'm going to be teaching it sort of on the along the way. A lot of people are scared of assembly language because it's so there's just so much, and it's not obvious what things do. But truly, once you get into it, it becomes pretty simple. The deal is with assembly, it gives you building blocks, and you can create things with it, but you have to build every little thing from scratch. And so it can be a little daunting, but it can be a lot of fun too. So you're not expected to know a whole lot. I would say I'm going to be glossing over some of the things with binary and hexadecimal and things like that. As I'm writing the code, I'll be going into what things do and try to explain as much as I can. I will probably be glossing over some of the details because, in fact, I don't know all the details. Again, I am not an expert here. And if you know more information than I do or that I'm saying, definitely leave a comment below. I'd really appreciate it. The tools that we're going to be using, the 3 things that we need an editor, we need an emulator, and we need an assembler. So for the editor, I'm using VS Code. I'm also doing this on Windows, but you can do this on Linux or Mac or whatever you're on. You could actually do all this work natively on an Atari computer. There's nothing stopping you from doing it as well. I prefer, doing it on the PC. It's just a lot faster and a lot easier to deal with. The emulator that we're going to be using is called Altera. It's a really good emulator for Atari 8-bit stuff, so it's going to work great for us. The assembler we're going to be using is called MADS. And so there's lots of different assemblers for Atari 8-bit. This is the one that I picked, and it's working pretty well for me. So the first tool we're going to need is VS Code. So I'm just going to do a search for it. VS Code right here, Visual Studio Code. Okay, so we're going to do a download for Windows, and it's going to automatically download, not a problem. The next thing we're going to need is Altera. So I'm just going to do a search for Altera. I'm going to do a search just to add emulator on there just because. And so we can look down here and we can get the latest version, Altera 3.90. You don't need the latest version, but might as well grab it. And the next one is going to be MADS. And there's actually a site called WUSDN. It is actually an Eclipse plugin. And I personally don't like Eclipse, but the idea here is that they have a package in here to be able to download all of the assemblers. And that's what we want to do here. We can go to the WUSDN IDE, and then you can go to installation, and then there is a section down here that says, alternatively, you can download the single archive containing all supported 6502 compilers. I should say assemblers there, but that's okay. So the idea here is that this is actually a zip file that has an ASM directory here, and we're just going to be using MADS. So you can just copy that directory into your C drive, because that's a decent place for it. And actually, I've already done that. So I actually have Altera already installed it's in the C program files directory. And so we can just go ahead and go in there. Altera is right here. And then we have MADS right here. And then we have VS Code already installed. I'm going to go ahead and fire up VS Code. Let's create a Hello World program in 6502 assembly. I'm going to go in here and I'm going to say open folder. Also, I'm going to be putting this up on GitHub. And so for each video, I'm actually going to create a new branch, so you'll be able to see where we are for each video. So if you want to follow along, that's a great way to do it. So I'm going to call this program EdVenture. And, like everything else on this channel, it's usually a pun on my name. And so why not? Sounds good to me. So we're going to create it. It's called EdVenture, and we're going to select that folder. And we don't need this welcome screen, but what we do want to do is create our first assembly program here. So I'm just going to call it main.asm. Okay, you can use asm.s or really anything you want, but the two common ones are asm and n.s. But yeah, you can use whatever you want. So let us start. So we're going to add some comments. Okay, so first off, a comment in assembly language just starts with a semicolon. So you can do it at the beginning of the line and the line wherever you want. One of the things you got to realize in assembly language is all of the statements that you're going to be writing are going to be starting one tab in or space or whatever you want, but it has to have some white space at the beginning. And there are some exceptions there, and we'll get into that. But the first thing we have to do here is we have to tell the assembler where our program is going to be living in memory. And this is going to be on the Atari system. The Atari has a memory map. We can actually look that up online. So we can actually look up Atari 8-bit memory map. And there's lots of books out there. Atari Archives has a lot of stuff in here. But basically, it'll tell us where everything is in the ROM of the machine. And each memory location actually has a label associated with this stuff. So some of these things, we're not going to be using most of this. We are going to be using a few. But the first thing is we need to figure out where our program can live. And a good place, and if we look through here, we're looking at the second column here, which is the hexadecimal number for where these memory locations are. One of the things is we don't want to put our program in a spot that it's not supposed to be in. We need to be writing this into RAM and not trying to write it into ROM, etc. So we're going to be using the location of 2000 in hex, okay? And the way we do that is we use org. So this is an origin line in the assembler, and it says we are going to put our program starting at the location of 2000 in hex. There's lots of different places you can put your programs. 2000 is a pretty good place. Obviously, if there's better places, let me know, but that's like the first available page that makes sense to be able to put your program. You can put it before then, but I don't think we're going to need to. The main thing here is we need to tell our program, or the assembler, where our program is going to live. Now, the next thing we're going to want to do is, so we're wanting to do a Hello World program, right? And so the idea with a Hello World program is we're going to want to output to the screen. In order to output to the screen, we need to know where the screen is located in the memory, okay? The one we're going to want is called SAVMSC, okay? So I'm actually going to do a search for that in our memory map here. And I'll link this in the description as well, the memory map. There's lots of different ones out there. This is just one of them. So this says the lowest address of the screen memory corresponding to the upper left corner of the screen where the value at this address will be displayed. So we're going to actually save this as a label here so we don't have to know what this is. So what we can do is we can type, this is one case where you want to put it on the left hand side without tabbing in. So I'm going to say save MSC equals, and we're going to say it's at address 58 hex, okay? And I'm going to just go ahead and put a comment here saying where the screen memory address is. Okay. So this is the memory address where our screen is, where the screen memory is located. So it's indirect, as in there is an address in this location, in this 58 and 59, if we look right here, at 58 and 59, that is where our screen is located. Now, the thing is, that's changeable. And that's going to be something we're going to need to do later on. The idea here is that we can say, this is where our screen memory is located, okay? It's going to be stored into this memory location, 58. Okay, so what we're trying to do here is we're trying to put in a hello world or some text on the screen, okay? So I'm going to go ahead and, a lot of times you put that kind of stuff in a data section of your program. And a lot of times it's at the end. It's typically you put all your instructions at the top and you put data at the bottom. That's just the way it works. So I'm just going to go ahead and put a comment down there saying this is data. And we're going to put a label on here and call it hello, okay? And we could call it whatever we want, but we're going to call it that. And we're going to create it as a byte. Now, the idea here is that we're going to have some text in here. So I'm just going to say hello Atari, okay? So we're going to be storing this hello Atari at this, we're going to be calling it hello. Okay, so this is going to be stored in our program at the end of our program, and we'll be able to refer to it as hello. The assembler will know where that is in our program, and we can refer to it as hello. We don't have to know the exact memory location for it in our program, but just so you know, where it would be located right now is actually at 2000. Because this is actually not stored in the program, because this is it's an assembler thing. It's called an equate, Basically what this is saying is that we're going to set this memory, this variable, so to speak, to this number. And all that's doing is saying anytime you see this, replace it with this. The assembler, that's all it does, okay? So the idea here is that currently right now we don't really have a program, but we have something. And at memory location 2000, it's going to store this H, okay? And then at 2001, it's going to store E, etc. So we're going to have this hello Atari in that location. Now, we're going to put some stuff before then, but the idea is that in our program, we're going to have hello Atari in there. So the next thing we need to do is we need to take these bytes right here and we need to copy them to screen memory. Notice we talked about this screen memory address, right? And so we don't know what the value is in here, what the screen memory is. We just know it's stored here. So we need to get that value. And the way we do that is, so we're gonna get into the whole idea here of how we're going to be interfacing in assembly. There's going to be two main things that we do in almost all of our assembly language stuff, and that is loading from memory locations and storing into memory locations. That's like most of what we do when we're doing assembly language. Now, obviously there's stuff we can do. We can calculate, we can do things like that, so that if you want to do some calculations on a number, you can. But the idea is that we have to load it in and we have to store it, okay? There are what are called registers in a 6502 processor. There's 3 registers. There's the X register, the Y register, and the A or accumulator register. X and Y are typically things you use for looping and stuff like that. A is your main like storage, your temporary location, okay? So that's a typical thing. Now you can use each one of them somewhat interchangeably. There are some instructions that only work with X, only work with Y, and only work with A. The one we're going to be using right here is going to be one that only works with Y. But the deal is here is that we're going to want to load into the accumulator. So that LDA means load, and sometimes you'll see it something like this. Load accumulator, okay? LDA. These are called mnemonics, okay? And we could get into how the assembler works and all that, but there's lots of other instructional videos on that. The deal is that we're going to be loading something into the accumulator, into that A register, okay? And what we're wanting to load in is this H, okay, to start off with. What we want to load is the whole thing, but we have to deal with things at 1 byte at a time, okay? So what we can say is we can say LDA hello, which is this memory location is down here, like we said. That's going to load what is in here into the accumulator, okay? So currently, if you did this, if we ran this, it wouldn't do anything yet because, but all it wouldn't show anything, I should say. It would load in this capital H into the accumulator and be done, okay? Not very useful. But what we want to do here is we want to store what is in that accumulator into our screen memory location. Now, if you remember, that is stored in this SAV MSC, okay? So what we do here is we can say STA, which this is store accumulator. So we have load accumulator, store accumulator. It might take a minute for you to wrap your head around what each one of those do, but the idea here is that we're putting something in with an LDA into the accumulator, and with the STA, we're taking it out of the accumulator and putting it into some memory location, okay? Now, what we're gonna do here is we're gonna say SAV MSC, and we did it with parentheses, okay? Now, the reason why we did it with parentheses, okay, so there's 2 ways you could write this. You could say STA, SAV, MSC. Now, that would be incorrect because what we would be doing here is we would be putting an H in this memory location of 58. We probably don't want to do that because this is where it's stored. Our memory location for our screen is located. What we want to do is we want to grab the data that's in there, this 58, and we want to use that data indirectly. Okay, so that's what these parentheses mean, in that we're doing what's called indirect addressing. And that is, we're saying what is in 58, we're going to be grabbing that out of it and using that. So we're going to be storing this into that. One way to look at it, if you're familiar with other programming languages, would be like a pointer, okay? So the idea here is that we're going to be storing this H into our screen memory right here, okay? So right now, what we have is we have an H loaded in to the accumulator, and then we're taking the H, or the H, and we're going to stick it in the screen. Now, one of the things we also want to do here is we want to kind of have an endless loop at the end here. We don't want to, we want to give the processor something to do after we do this, because the program, it's not like a normal program where it can exit. There's not really any of that concept on this kind of machine. So we need to give the processor something to do. So I'm going to show you one more command here, and that's a JMP, which is a jump. That is a jump to a memory location. So this would be equivalent to a goto. And if you use a star, that means jump to itself. Okay, so the idea here is that it's going to do these things and it's going to continuously go right here. So it's just going to just sit there forever. And that's exactly what we want. So this will put an H into the first memory location on the screen. Okay, now let's go ahead and run this. Now to start this off, so I know we want to do the whole Hello Atari, but I want to show you the very bare minimum that we can get by with. Okay, so first thing we're going to want to do is we're going to want to assemble this program. Now, if you have everything set up correctly and you can set up your path so that MADS is in your path and Altera is in your path, I can set up another video if you need me to show you how to do that. There's probably tons of videos on there how to do that. But the idea here is I want to be able to just type MADS, okay? And so we actually have a comment on here on how to do this. So we can say MADS, and I'm just going to call it, I called it main.asm, and then we have EdVenture.asm. I need to fix that comment. That's okay. Okay, so we have an error. It says illegal addressing mode. So it doesn't want to just store it at this location. That's okay. What we need to do is we need to do one more step here. And that is we need to tell it for the indirect addressing mode, we need to have another variable in here. And what we're going to have is called, we're going to use the Y one. So what we're going to do is we're going to put 0 into the Y register. A reason why we have a pound sign here, what that means is that by default, if you used like 0, that would use whatever's at that memory location. We don't want that. What we want is a literal 0 to go into the Y register. Now, so in order to use this indirect addressing mode, we need to have something in the Y register to be able to use this. That's okay. So we should be able to run it now, hopefully, theoretically. Cool. So we are able to write the listing file and the object file. And if we look at this, we have a main.obx, which is currently 28 bytes long. Very small. Okay, and what I want to do is I want to run it, and the way we run it is we actually, I have, going up here, what we can use is Altera single instance, and I'm just going to change this here to main.obx, okay? Now, so we see H, and that's actually what we expected, right? So yeah, so we now have an H on the screen. Not very exciting. We want the whole thing, right? So in order to do that, we need to do a loop. Okay, so what we want to do is we want to go H, then E, then L, and all the way through, right? So the way we're going to do that we actually have almost everything we need already. What we're going to do is we're going to create a label. We're going to call it loop. Okay. You can call it whatever you want. And we put this on the left-hand side. It does not get tabbed in. Labels always go on the left-hand side. So labels and equates are the only thing that go there. So I had said earlier about the fact that there are some exceptions. These are the exceptions. So what we're wanting to do here is we're wanting to add a comma y here. This comma y is what's called an offset. Okay, so what it's going to do here is it's going to say at this memory location of hello, comma 0. So it's actually going to be plus the y value here. So we already used this before, and that's still 0. But what we're going to want to be doing is we're going to want to be increasing y each time. To do that, we're going to be using an INY mnemonic, and that means increment y. And so what we're going to be doing here is at this point, it says that y is equal to 0. And so basically at this point, we're going to ignore loop, and we're just going to say LDA hello, comma 0, which is going to be, the H still. And then what we're going to do is we're going to store it in the screen memory that we said, and with an offset of 0. So plus 0. Now we're going to increase y. So it's going to be now equal to 1. And what we're going to do here is that we're going to want to loop. And the way we're going to do that is we're going to want to loop a certain amount of times. And so the way we can do that is we want to use the compare mnemonic here. And that is compare with y. And what we're going to say is we're going to do 12, and that is we're going to use 12 because there are 12 characters here. And the idea here is that we're going to say increase y and then compare it with 12. And then we're going to use BNE, which is branch not equal. And we're going to say branch not equal loop. There's a specific register. We talked about A, X, and Y, but there's one more actually called the status register. And the status register is kind of interesting in that I'm actually going to go ahead and bring it up here. 6502 status register. It has, the deal is we don't use the status register directly. And basically what we care about is just a few of the bits in here. So we have the N bit, the V bit, the B bit, D, all these different ones. And they actually have names. We have the negative flag, overflow flag, break flag, decimal flag, interrupt mask, 0 flag, and carry flag. Okay. The one we care about here is the 0 flag. Okay, so let's look up BNE on the 6502. And the BNE instruction, I can search here, has to do with the Z flag. Okay, so that is the 0 flag. When you use the CPY, what it's going to do is it's going to compare, and it's going to set that 0 flag to either 0 or 1. And the idea here is this B&E, if you look here, it says if the flag is 0, then B&E will branch. If it is equal to 1, it won't. So the idea here is that we're going to do this comparison with 12. Each time it's going to be equal to 0 until we get to a point where this is true. So CPY 12 means it's going to compare y with 12. And the first time through, it's going to be 0. Actually, at this point, it's going to be 1. Is it 12? No. Okay, so we're going to do this loop. It's going to go to 2. Is it 12? No. We're going to go through this, 12 times. And then when it does equal 12, then what it's going to say is when it does this comparison, it's going to put a 1 in there, and then it's going to just jump out of this loop. Effectively, this is not going to trigger, and it's just going to go right past it. So that's how we break out of this loop. So I'm going to go ahead and assemble it. Awesome. So we now have Hello Atari. This is how we can get Hello World or Hello Atari to the screen. Hope you enjoyed the video. If you did, be sure to hit the like button. And if you'd like to see more of this series or any of my other series, definitely hit the subscribe button and ring the bell. I post new videos at least once a week. Until next time, see you in the next adventure. Take care.